All right, so for question number 1 here, okay, we're looking for the position of the object after 1 minute. So anytime we have a graph and we're given the equation of the line asking us to calculate something, we need to figure out what part of the equation are we looking for. Okay? In this case, it's asking us calculate the position. Which axis is position on?
Y.
Okay, it's on the y-axis, which means I'm solving for y. I'm solving for a y value that occurs at 1 minute. Okay, now, where is time? X. So this is giving me the value of x. So I'm supposed to calculate y when x is 1 minute. Okay, or in this case, 60 seconds, because on the y-axis is seconds. Okay, or sorry, x-axis is seconds. So I just need to plug into my formula here. Okay, x equals 60, so y equals 3.85 times 60 seconds minus 0.801, or plus negative 0.801. Okay, works out the same either way. All right, so if I do that, 3.85 times 60 plus negative 0.801. All right, so it's going to have traveled 230.2 meters. Okay. All right. To the proper number of significant digits here, I think we'd be looking at 2.3 times 10 to the 2. Right? Since we never used any of these that have only one significant digit, we're good. Okay. Everything we used had at least 2. All right. For question number 2 on this question, okay, it's asking how long it'll take. So now I'm being asked to calculate x, okay, because time, how long, is on the x-axis. So that means then I've got to manipulate the graphing equation to solve for x. Okay, so I'm going to subtract b from both sides, okay, and then I'm going to divide by m, and that'll leave me with x. Okay, they told me that the position is 150 meters, so y equals 150. So 150 minus negative 0.801, okay, divided by m, which was 3.85. Okay, so we're looking at 39 seconds. Okay, everybody all right with that? Okay, is that ringing a bell for math and science 10? Okay, so here's another position versus time graph. This one has 3 carts on it. This is actually very much like what we're going to be doing on Monday when we do our first lab on position versus time graphs. Okay, so I want you, using the equations for the lines there, so okay, for cart 1, y equals 1.38 times x plus 9.52 times 10 to the minus 3. For cart number 2, it's 2.01 times x plus negative 0.0524. Okay, y equals 3.39. All right, so you got the equations for each cart. Okay, I want you to answer those 3 questions about each cart. So you're going to be doing 3 things for each question. Okay, let's, oh, I left that recording. Okay, let's quickly look at number 1. If I asked you question number 1 on a test, what would each one of them be out of in terms of marks? Okay, the velocity of each cart would be worth 1 mark because you have to do absolutely nothing to get it. Where can I find it?
M.
Yeah, it's the slope of the line. Okay, this is what we were talking about yesterday. We got to be able to analyze a graph in order to figure out what it gives us. Okay, because this is a position versus time graph, okay, the velocity of the cart will be represented by the slope of the line. Because when I calculate the slope of the line, I'm taking the object's final position, subtracting its initial position, y minus b, divided by the total time, x. Okay? So all I had to do to get all the answers for question number 1 was go 1.38 meters per second, 2.01 meters per second, 3.39 meters per second. And I'm done. Okay? But that's me being able to analyze the graph, not necessarily looking to do a calculation. Now, I would imagine that probably a lot of people were squinting away at this graph, and they were trying to figure out what the value of this point right here was. And I purposefully made the graph so that you couldn't do it that way. Okay? You would have to estimate big time to figure out what that would actually be. I have no idea what it is. Okay? So what I was looking for you to do, okay, was simply to do the graphical analysis rather than try and do a v equals d over t calculation using numbers you had to grossly estimate. Okay? Here's the big tip. If a question gives you the equation for the line, use it. Don't try to do anything else. A question would never give you the equation for the line if it wasn't important, okay, and basically necessary for you to do the whole thing. Okay, so spoiler alert, that means 2 and 3 require you to use the equation for each line in order to get the answers. Okay, does everyone follow what I did there for number 1? Okay, keep going. So we are looking for the position of each cart after 12 seconds in number 2, which means we're solving for y or x? Y, okay, because position is on the y-axis. And they gave us 12 seconds, which is an x value because time is on the x-axis. All right, so all we have to do is plug in, okay, m, so for cart number 1, it's going to be 1.38 times 12 seconds plus 0.00952, okay, and then we have our answer. So that would be for cart number 1, okay, and for cart number 2, we'd be looking at 2.01 times 12 plus negative 0.0524, okay, and for cart number 3, okay, we'd be looking at 3.39, again, times 12 plus 0.0381. And so for our first one here, 1.38 times 12 plus 0.00952, and it gives us 16.6 meters. Actually, we'd only have 2 significant figures there, so it would be 17 meters. Okay. And probably would be positive. We weren't given a negative on here, but okay. And then for our next one, 2.01 times 12 plus negative 0.0524. Okay, so we're looking at 24 meters. And for number 3, we're looking at 3.39 times 12 plus 0.0381. Okay, so we're looking at 41 meters there. And that makes sense because the fastest cart was cart 3. It should have gone further than the other ones. Okay. All right, how many people have done number 3? Okay, all right, let's quickly have a look at number 3 then. Okay, so on number 3, okay, we have the other manipulation. We're looking for how long it'll take to get to a position of 50 meters. Okay, so that's going to mean we're solving in x1 that we're going to have y, 50 meters, minus b, which was 0.00952, and it was negative. Okay, so there's y minus b over m, which was 1.38. Okay, for our second cart, okay, x2 is going to be 50 minus negative 0.0524. Sorry, was that 0.952 negative? Or was I wrong? No, it's not negative. Okay, and then we're dividing that by 2.01. And then for the third cart, we're looking at 50 minus 0.0381 over 3.39. Okay, so 50 minus 0.00952 divided by 1.38. Okay, it's 36 seconds. Okay, for our second one, 50 minus negative 0.0524 divided by 2.01. All right, 25 seconds. And for our last one, 50 minus 0. How was it? 381 divided by 3.39. All right, so looking at 15 seconds for that. All right, and those answers make sense. Fastest cart should take the least amount of time to go 50 meters. Okay, is that ringing a bell? That is exactly what the analysis on your lab on Monday is going to ask you to do. And by exactly, I mean it'll be a different graph because it'll be your data, but the questions will be exactly the same. Okay, so what we just did today is the analysis for your lab on Monday. Okay, so there shouldn't be any problems because I'm recording this, and you can totally go back and watch it so you know what to do. Because sometimes I'm a nice guy, sometimes I'm not. Today I'm nice. Okay. So this one doesn't have an equation. Okay? This one's an irregular graph, so we won't be using y equals mx plus b here. Okay? See if you can calculate for me the total displacement, total distance, average velocity, and average speed. The answers are there in bold, so you'll know if you did it right. Okay, I'll give you a couple minutes to try that one, see if you remember what we did with those irregular graphs yesterday. So if I want to calculate my total displacement, okay, I have to remember that total displacement can be calculated by taking final position minus initial position. Okay? I can't use y equals mx plus b because they don't have it. And this is one single line. Okay? So my final position is positive 0.5 meters, and my initial position is positive 0.2 meters. So okay, 0.5 minus 0.2 is going to give me positive 0.3 meters. All right with what I did there. If I want to find the total distance traveled, now I got to figure out how far does it go in each section of the graph, okay, because distance is scalar, it doesn't care whether I backtrack or not. Okay, don't go anywhere here during the first second, okay, but then I go from 0.3 to 1. So that's 0.7 meters. Then we don't go anywhere because it's stationary. And then it goes from 1 down to 0.5. Right? 0.7 plus 0.5 is going to, oh, sorry, that's 0.8, not 0.7. It went from 0.2, not 0.3. Okay, so it's going to be 1.3 meters in total. Okay, we're all right with that? All right. Now that we have the total displacement and the total distance, we can very easily calculate the average velocity. Okay? Average velocity is total displacement divided by total time. Positive 0.3 meters divided by 7 seconds is going to give me 0.04 meters per second, and that'll be positive. And then for my speed, distance divided by time, okay, that'll be our 1.3 divided by 7 seconds, and that's going to be 0.19 meters per second. Are you all right with that? I wouldn't give you anything more difficult than that on, let's see, like a unit exam where I ask you to analyze a graph. Yeah, that's pretty. Okay, let's try this one and then we'll move on to velocity versus time. Okay, so we got displacement, it's position versus time. Okay, every box on the x-axis is 1 second, so 1, 2, 3, 4, 5, 6, because I know it's hard to read the lines there. Okay. Give you a couple minutes on that one, and then we'll move on to velocity time. The displacement between 0 seconds and 4 seconds, okay, our final position is -4, our initial position is 0, so our total displacement is -4 meters between 0 and 4 seconds. Okay, the distance traveled, the total distance traveled. All right, well, we go 4, 0, and then from 4 to 6, that's 10, 14 meters, total distance traveled. Okay. And then the average velocity over the whole trip, which requires us to do the total displacement over the whole trip, which is 6. Okay, so we got 6 over 6, 1, no. Sorry, we got, sorry, average velocity, yeah, it is 1 meter per second. Sorry, I jumped ahead, I did D instead of C. Okay, so the average velocity over the whole trip, okay, our total displacement is +6, okay, our time is 6 seconds, so +1 meter per second, and then our average speed over the whole trip is going to be 14 over 6, which is going to be 2.3 meters per second. Okay, good with that. Okay, so velocity versus time graph should also be a bit of review from Science 10, because we did go over those in Science 10, and I'm not going to ask you to do anything different in Physics 20 with these graphs than you did in Science 10. I might explain something a little bit different just because we look at it in a bit more detail. All right, so the two graphs that are on this slide, one of them is a position versus time graph, one of them is a velocity versus time graph. Okay? What is the position versus time graph showing? Okay, so it's showing that it's traveling at a constant velocity? No. Okay, our first graph is showing that the object is traveling at a constant velocity because the position changes by the same amount every second, right? It's a linear function, so this is an object traveling at a constant velocity. What's the velocity versus time graph showing?
It's also a constant velocity.
Right, it's also showing an object traveling at a constant velocity. In fact, it's the same object. These two graphs are of exactly the same motion. They're just looking at it from different points of view. Okay, so I can prove that here pretty quickly. If I calculate the slope of this line, it'll give me the velocity of the car, or the object. Agreed? Okay, so let's do that really quickly. Okay, B is 100, right down here. Okay, so B is 100. I'm going to take this as my Y value, 1400. Okay, so I'm going to have 1400 minus 100, so there's Y minus B, divided by X, which is 5 seconds. That should give me 260 meters per second, right? 1300 over 5. Okay. Is that about where the line is on that velocity versus time graph? They're graph of the same motion. Okay? In the case of the velocity versus time graph, it's not changing velocity. It's showing the object's velocity not changing, so traveling at a constant velocity. Everybody with me there? Okay. If it's traveling at a constant velocity, what is its acceleration? 0. Right? Acceleration is a change in velocity over time, or it's the rate at which you change your velocity. If you're traveling at a constant velocity, you're not changing your velocity, thus your acceleration is 0. Okay? So that line there has a slope of 0. It's flat, right? Horizontal, so it has no slope. Okay. So why am I bringing up slope? Why am I bringing up slope on this graph when it has no slope? Okay, I'm bringing it up because we just looked at some examples of a position versus time graph's slope being equal to velocity. Well, the slope of a velocity versus time graph is the rate at which velocity changes. In other words, the acceleration of the object. Okay? I think I showed you this yesterday. Okay, but if I'm looking at a velocity versus time graph, and let's say that my velocity versus time graph looks like this instead. Okay? Would that object be accelerated? Okay. If I calculate the slope of that line, that'll be the acceleration of that object. Okay? And here's why. M equals y minus b over x. Y is going to be my final velocity, because that's what's on the y-axis, is velocity. B is my velocity at time 0, or my initial velocity. Okay? And what's on the x-axis? Time. Okay? Is that the formula you used last year to calculate acceleration? That's where it comes from. Okay? So again, it's just graphical analysis. I don't have to memorize that the slope of the line on a velocity time graph is acceleration. I can figure it out. Okay. All right. Could I calculate the displacement of that object from the velocity versus time graph? I mean, I calculated the displacement on this graph really easily, right? I went 1,400 minus 100, and I got it was 1,300 meters. Okay? This graph doesn't show me its position. So how do I calculate velocity, or sorry, displacement, if I know velocity and time?
And multiply your velocity by
Exactly. Okay? I just use this formula. Average velocity equals displacement over time, and I solve for displacement. That means I multiply my average velocity by time. On this graph, my velocity doesn't change, so my average velocity is 260 meters per second. And it does that for 5 seconds. 260 times 5. It's the same number I got on the other graph. Okay? Now, here's what you might have memorized last year in Science 10. The displacement is the area under the line. For how many people does that sound familiar? A little bit. Okay? Here's why that works. It's why we kind of teach it to you in Science 10. It's because it works. Okay? But it's also because it's true. If I find the area of this, the area underneath this line, it's a rectangle. Okay? How do I calculate the area of a rectangle? Length times width, or base times height, right? Same. Okay. What's on the base of this rectangle? Time. What's the height of this rectangle? Velocity. Is that formula right there? Okay. All right. Does it still work if, whoops, not that. Does it still work if the graph looks like that? It does. It still works. Okay? I can still calculate the average velocity in the same, or sorry, the total displacement by taking average velocity and multiplying by time. But my velocity is changing on this graph. Okay? So how do I get the average? Let me put it differently. How do you calculate the area of a triangle? Base times height divided by 2. Okay. So I take the base, and then I multiply it by my height, but the height over 2. Well, if I start at a velocity of 100 and get to a velocity of 400, is my average velocity smack in the middle of those two numbers? It is. Half the time I'd be going faster than that, half the time I'd be going slower than that. My average is right in the middle, which is why if I take the height of this triangle and divide it by 2, it gets me the number smack in the middle. Okay? So it works. It's a little trick. The problem is people memorize it and then they apply it to the wrong graph. Okay? In this case, it works because of what we're doing. We're looking at time and velocity, and we're multiplying them together. Okay? We don't want you to necessarily memorize the area under the line anymore. We want you to be able to analyze and get to that. There's how we analyze. Okay? Does that make a little bit of sense Okay, when we start talking about acceleration, we're also going to look at a new acceleration formula, and it looks like this. Okay, this acceleration formula calculates the displacement of an accelerating object, and it does it using what we just did. Okay, so if I've got a graph, a velocity versus time graph, that looks like this. Okay, and I want to calculate the displacement. We learned it's the area under the line. Well, the area under the line is two different shapes now. There's a rectangle, and then there's a triangle on top of it, right? It's got to be the area between the line and the x-axis. Okay, so now there's two shapes. How do I calculate the area of a rectangle? Base times height. What's on the base? Time. Okay, the height of this rectangle, would that be the y-intercept? Would that also be my initial velocity? And I'm going to add to that the area of the triangle, which is 1/2 times the acceleration times time squared. It's a roundabout way of getting the area of the triangle. Okay, but this here gets the area of the triangle, okay, and solves for the same thing. Right? If I gave you that graph and the equation y equals mx plus b for that, you'd be able to do it. Okay, we're not there yet, but we'll get there. Okay. All right. The velocity versus time graph stuff ringing a bit of a bell. Okay, that's really about all we're going to do with a velocity versus time graph is calculate displacement, calculate acceleration, and probably have some y equals mx plus b stuff as well. Okay, so if I gave you y equals mx plus b, I would ask you to calculate how fast will the object be going after a certain number of seconds, or how long does it take to reach a certain velocity. And you'd be solving for y, solving for x, in the same way you did on a position time graph. It's just that y represents something different. Now it's velocity instead of position. Okay, here's a velocity versus time graph of somebody running like a sprinting race. Okay, what are they doing at the beginning? They're accelerating, okay? And it's not uniform, right? There's a little bit of a curve there, okay? And that's actually pretty accurate. When you come out of the starting blocks, there's a little bit of like, slippage and stumbling and stuff as you come out of the blocks. Okay, it's not the most smooth acceleration, but once you get your feet under you, the acceleration is very smooth. If you've ever watched a 100-meter race in slow motion, you can actually see this happening, especially if you watch Usain Bolt. Okay, the guy is like amazing to watch. I can't even think of a word to describe it, but it's just perfect when you watch him. Okay, so you would be accelerating, accelerating, accelerating. Okay, then you get to here. Doesn't matter how hard you push, you can't run any faster. You've reached your top speed. Okay, and runners hit this at some point in a 100-meter race. Okay, in a 100-meter race, they typically accelerate for about 2/3 of the race. Okay, and then they run at their top speed for about the last 30% of the race or so. Okay. So we're going to run at a constant velocity here, and then what happens here? Slow down and stop, because my velocity actually becomes 0. Okay, so again, that's just asking you to interpret a graph, being able to look at that graph and say, here's what's going on. Okay, important skill for us to do. Okay. All right, so this is kind of a weird one because this person actually only accelerates for half and then runs at their top speed for about half. Okay, and it takes them about 10 seconds, and they're quite slow. Okay, like I know 8 meters per second. I mean, it seems like a lot, but Usain Bolt runs at 17 meters per second at his top speed. The guy is freakishly fast. Okay, at his top speed, he is running from that wall through the lab. When you're 6'8" and super fast, you can do that. Okay, it's actually like really funny to watch his competitors because though Usain Bolt is a terrible starter. If you've ever watched any of his races, he's like the last guy out of the blocks. He looks lackadaisical. Okay? He slowly accelerates. Everybody's ahead of him, but you can see them all at about 2/3 of the way through the race starting to tighten up because they can hear his footsteps. They just know he's coming. Okay? Because he's just that fast. His top speed is ridiculous. His acceleration is terrible for a world-class sprinter. Okay? He'd kill any one of us, but okay, his acceleration is terrible for a world-class sprinter. He just gets to top speed, and his top speed is so much faster than everybody else's that he just reels everybody in. Okay? By the end of the race, that's why the 200 is actually his better race. Okay? He reaches top speed and maintains it for like 150 meters. Nobody can touch the guy in a race that long, okay? Because he doesn't tire out. That sort of making sense? It's strange, but it's like, it's totally physics. And when you watch him in slow motion, you can actually see like the graph almost as he runs. It's crazy. All right. So on a velocity versus time graph, the things we can read directly off are obviously velocity and time, because that's what it's showing us. Okay, we know that we can calculate acceleration because we would have initial and final velocity, and we would have time, and we could calculate it from the slope, or we could just use this formula. Okay, if it's one single line, then obviously we would calculate the slope. But we could get a velocity versus time graph that maybe has a couple of sections. Okay, something like this, and they'd say, what's the acceleration over the whole trip? Well, then I would have to look at what's VF, what's VI, and what's my total time. Okay, we might have to do it that way. It's no different than calculating the average velocity over the whole trip for a position versus time graph that's irregular. Okay, and then we were talking about this, the area under the line part. Okay, the reason that works is because it's really just a manipulation of either V equals D over T, or the new formula that we haven't learned yet, D equals VI times T plus 1/2 AT squared. Okay, either one will work. Okay. All right, I think we'll give this one a try. So a snowmobile is moving according to the graph, okay, here. So don't worry about this part. That's not what we're working on. Okay, so the snowmobile is moving according to that graph. Okay, and I want you to find the snowmobile's I don't want you to calculate that stuff. I want you to calculate for me instead. Okay, I want you to calculate the snowmobile's average acceleration over the whole trip. Okay. And total displacement. Can you guys read that graph, or should I make it bigger? Let's just do this. Easier to read now? Okay. Average acceleration, total displacement. Okay, so to calculate acceleration, okay, we just want to use our acceleration formula. A equals final velocity minus initial velocity divided by time. Okay, in this case, we're talking about the average acceleration over the entire trip, because obviously it accelerates during two parts of the trip, and then during one part of the trip it travels at a constant velocity. But overall, it accelerates. Okay, so we want to calculate that average acceleration. So that's going to mean 80, our final velocity, minus our initial velocity, 0, divided by the total time, 60. Okay, so 80 over 60, which would be 1.25. No. All right. I shouldn't do math in my head. 1.3. See, that's why I shouldn't do math in my head. 1.3 meters per second squared, and that would be positive because it is increasing in velocity on average. Okay. Incidentally, would that be the slope of that line? that would be the average acceleration over the entire trip, right? I mean, on average, that's essentially what it did, okay, over the whole trip. Let's do that. All right. And then how are we doing on displacement? Can we move a couple more minutes on displacement? No? Okay. All right, so for displacement, okay, we've got to kind of look at what's going on in each section of the graph. There's this section of the graph right here where the object is accelerating. So the average velocity is changing and would be half the height of this triangle. Okay? Then during this part of the graph, the object's traveling at a constant velocity. But I also need to take into account how far the object would go if it continued to travel at a constant velocity. So I've got to extend that rectangle all the way to the end. Okay? And calculate what? Is there one more part I'm missing? No. The triangle above it. Okay? Because this is how far, this box is how far it would go if it continued to do this, travel at a constant velocity. But it goes faster after that, so I also need to take into account how far it goes while it's accelerating and add that on. Okay? That's why I'm doing all three of those shapes. Okay? So this first one here, we're going to have a base of 20 times a height of 40 over 2, so we're looking at 400 there. 20 times 20. I should probably know. See, I said that twice now. 20 times 40, yeah, divided by 2 is 400. Okay, and then I've got this rectangle here that goes from 20 to 60, so the base is 40. Okay, the height is also 40. Okay, so 40 times 40 should be what, 1600? Okay. And then I've got this little triangle here, okay? The base of it is 10 seconds, and the height of it goes from 40 to 80, okay? So its height is 40. So 10 times 40 is 400, divided by 2 is 200 meters. All right, so I've got 2,200 meters. That's my total displacement. Good there? All right, that's as good a place as any then, because it doesn't go anywhere.
Isn't the second triangle 40 meters tall? Or?
It is 40, but it's over 2. It's a triangle. 10 times 40 is 400, over 2 is 200.